In this video, we're going to be talking about section 9.2 from your textbook, where section 9.2, we're going to be constructing confidence intervals about the population mean. Remember, in the previous video in 9.1, we were constructing confidence intervals for a population proportion. So constructing a confidence interval for a population mean is going to be a very similar procedure, but just a little bit more sophisticated. And we'll see what we're doing shortly. Again, we'll start with some preliminaries. So we're going to assume x is a random variable that is generated by a normal distribution with mean mu and standard deviation sigma. A sample mean, x bar, remember from chapter 8, this is also going to be normally distributed. And it will have the same mean as the underlying distribution, but it's going to have a different standard deviation. So the standard deviation is going to be less than the underlying standard deviation because we're going to divide by the square root of the sample size. So whenever your sample size is larger than 1, the standard deviation of the distribution of the sample mean, that's going to be less than underlying distribution's standard deviation. And so we can also approximate this standard deviation of the distribution of the sample mean, so the lowercase s then represents the statistic for that parameter. And again, same idea, we just divide by the square root of the sample size to get that approximation. And so this is one thing we're carrying forward from chapter 8 that we need to know. And it turns out that this z-score, the one where I take my sample mean and I subtract the mean of the distribution and then I divide by the standard deviation of the sample mean, so it's the parameter version. If I happen to know this exactly, right? If I happen to know what that parameter is exactly, then we would say that this z-score follows the standard normal distribution. However, in practice, we don't know the exact parameter for the standard deviation, right? So whenever we take a set of data, we take a whole bunch of measurements about some random process, we can calculate a sample standard deviation. Remember, the sample standard deviation is just a statistic that provides our best guess of the parameter, which is the population standard deviation. So in real life, we don't know this parameter exactly. What we do instead is we can calculate the sample standard deviation, and that is actually going to be itself a random variable, because again, depending on the sample that you just took, you might end up with a different sample standard deviation. And so whenever you introduce this little bit of nuance, whenever you realize that the sample standard deviation is itself a random variable, then these, what looks basically like a z-score, we're going to call it a t-score, and it follows a different distribution. It doesn't follow the standard normal distribution anymore. It follows what we call the t-distribution. So sort of taking the same math that gave us the standard normal distribution, replacing the exact parameter for standard deviation with our statistic. If you really focus on the math, and we're not going to do this in this course because this would be something that like a graduate student in statistics would do, you can see that sort of the same mathematical processes behind the scenes gives birth to a whole new probability distribution called the t-distribution. Now here's some properties of the t-distribution. The t-distribution, just like the normal distribution, is symmetric. It represents a continuous random variable. It's mostly bell-shaped, but you might say that it has what we call, fatter tails than the normal distribution, or heavier tails. And there's a nice link here to a website that has a nice tool that I want to show you. So let's open that one up and see what we get. Okay, so here is, again, a separate website that you can go visit on your own. And what's cool about this is it shows you in blue the t-distribution. On top of this dark dotted line shows you what our standard normal distribution would be. And so you can see the difference in the shape, namely that around the center, the t-distribution has a little bit less probability density, and then in the tails, the t-distribution has a little bit more probability density than the normal distribution. So that's why I say the t-distribution has heavier tails. Now, just reason with me for a moment and consider that the whole reason this t-distribution is different from the standard normal distribution is because we don't know the standard deviation exactly. But you should also know that the larger my sample size, then the better idea I have of my standard deviation. Right? So the larger the sample size, whenever I go to calculate my sample standard deviation, I have more confidence that the standard deviation I calculate is closer to the population standard deviation. If I take a sample size of like 1 trillion measurements, I have an extremely high degree of confidence that my sample standard deviation is extremely close to the population standard deviation. And yet, if I take a sample of only 4 individuals, I really don't have very much confidence at all that the sample standard deviation I calculate is anywhere close to the population standard deviation. So like I said, like I always say, increasing your sample size to get a larger sample size is always a good thing for your statistics. It increases your accuracy for all of the statistics you calculate, and that your statistics become closer to the parameters they're trying to approximate. Okay, so that means if I increase the sample size, my t-distribution should look more and more like the standard normal distribution, because again, my sample standard deviation should be getting closer and closer to my population standard deviation. So let's see if that's true. And we're going to find that there's not just one t-distribution, but every single sample size you have generates a different t-distribution. And so on this slider, it says slide to change degrees of freedom. And right now, degrees of freedom is 1 in this calculation. But basically, degrees of freedom here is just my sample size minus 1. So if I had a sample size of 2, that would give me 1 degrees of freedom, and this is what my t-distribution would look like. But if I had a really large sample size, and notice as I increase my sample size from 2 to now 3, my sample size were 3, my degrees of freedom would be 2, and notice that the t-distribution for 2 degrees of freedom is much closer to the normal distribution, right? You can see the difference happening. Let's increase my sample size to 10, so my degrees of freedom would be 9. And that's even closer. Let's increase my sample size to 30, so my degrees of freedom would be 29. And let's increase my sample size to 100, so my degrees of freedom would be 99. And you can see closely by looking at the probability density curve up here that, as far as I can tell, the t-distribution and the normal distribution exactly match. Of course, that's not true exactly, but it does look very, very close. So basically, the larger sample size you have, the larger your degrees of freedom, and the closer your t-distribution is to matching the standard normal distribution. Now, what we're concerned about really is this plot down here on the right, where it tells you relative error if you were to use a standard normal distribution to approximate the t-distribution. So basically, a relative error that's much larger than, 0.03 or so, something really close to the bottom of this y-axis or this vertical axis in this bottom right plot, that's pretty bad. And these horizontal axis 0, 2, 4, 6, 8, that's in terms of standard deviations away from the mean. So even for a really large sample size, if you get much larger than, I don't know, about 2 standard deviations, then our calculation, if you were to use the standard normal distribution versus the t-distribution, that starts to introduce a relative error of 5 to 10%. That's pretty bad. And so while the standard normal distribution might work for really small deviations from the mean, it's not going to work well for larger deviations from the mean. And you'll notice whenever I lower my sample size down to 10, that relative error takes off even faster. And so if you have a sample size of only 10, you really can't use the standard normal distribution to approximate what's happening with the t-distribution, because the relative error departs so quickly from 0. You have a significant error even talking about just one standard deviation away from the mean. And of course, if your sample size is only 2, then the standard normal doesn't even approximate this well, even close to the mean. So if that was confusing to you, that's okay. That's not something you have to memorize for an exam. The key that I want you to take away is that there is a distribution called the t-distribution. The t-distribution looks mostly bell-shaped, but it's a little bit different from the standard normal distribution, right? It deviates from the standard normal almost everywhere, despite having something that looks like maybe roughly the same shape. In any case, let's continue on. When your textbook, or when I use this notation with a lowercase t subscript alpha over 2, what it means here is we're going to evaluate the quantile function, this time of the t-distribution, at the point 1 minus alpha over 2. So how do you evaluate the t-distribution using our calculator, our TI-84? We're going to go to second, VARS, and we're going to go to INVT, which is going to be number 4 on the list, because we're looking for the quantile function of the t-distribution this time. So punch that in. Area is where you're going to put in 1 minus alpha over 2, and you're also asked here for degrees of freedom. That DF stands for degrees of freedom, and like I've mentioned before, for us, degrees of freedom are going to be your sample size minus 1, so n minus 1. Here's an example. Suppose I want to measure my car's miles per gallon. So I take one measurement. Probably what I'm going to do is I'm going to fill up my tank with gas. I will reset my odometer. I'm going to drive in the city or on the highway, it doesn't really matter, until I'm completely out of gas and I need to refill. So I'll go back to the same gas pump. I'm going to refill my car's gas tank all the way back up to the top. I look to see how many gallons of gas did I just buy to refill my gas tank, and then I'll look at the number on my odometer. Since I reset it the last time I had a full tank of gas, that my odometer should tell me how many miles I've driven since I refilled my tank. So I have a miles measurement from my odometer, I have a gallons of gas measurement from the gas pump. I can divide miles divided by gallons of gas, and that's going to give me my miles per gallon, right? So MPG just stands for miles divided by gallons of gas consumed. And so doing that, suppose my car's miles per gallon is 33.2 miles per gallon. And I could just take that and walk away with it and assume that it's the correct miles per gallon. But I have one thought in the back of my head that maybe this isn't correct. Because maybe on my trip where I went through that tank of gas, maybe my car was towing a trailer with some horses in it, and maybe I was driving into the wind the whole time, and I was driving uphill the entire time. And, there's a lot of different factors that may have caused my car to use more gas or have a a lower miles per gallon than normal. So instead of taking just one measurement, maybe I should repeat this measurement over and over again several times. So maybe I repeat the process 7 times and I come up with 7 measurements like this. And they're all a little bit different, right? Because, you never expect any measurement to be exactly the population mean. And even when we go to calculate the sample mean, we don't expect this to be exactly the population mean either. So let's calculate the sample mean really quick. And to do this in my calculator, I like to go to Stat and then Edit. And then I'll punch in the first column all of these numbers. So I'm going to put in, let's see, 33.2 and 24.8 and 29.3 and 30.5, 28.4, 32.7. Oh, looks like my calculator really is having a hard time. Okay, so I got the numbers in my calculator in list 1. I go back to Stat, I go over to Calc, and I calculate one variable, statistics. Go down to Calculate again, and it tells me that my mean is going to be 29.8 for my sample mean. Okay, now remember, even the sample mean itself is a random variable. The sample mean will change depending on the measurements that we choose to include in the sample. So if I have driven other places, during the course of these, I would end up with different measurements, and then my sample mean would be different, right? So remember this formula from Chapter 8 for the sample standard deviation of the distribution of the sample mean, also called the standard error of the mean. And notice that a larger sample size is also going to reduce my standard deviation. This time in section 9.2, we're going to talk about 2 different ideas, a prediction interval and a confidence interval. So a prediction interval is going to contain 1 minus alpha times 100% of the most likely outcomes from a random process. And we're going to have this formula for the lower bound and this formula for the upper bound. And this confidence interval is talking about something different. The confidence interval is going to contain 1 minus alpha over times 100%, whatever percent that is, maybe 95%, right? Of the most likely values of the population mean. And so again, we have a lower and an upper bound formula, which is centered around our sample mean. Notice both the prediction interval and the confidence interval are centered around our sample mean, and we're adding in something for the upper bounds and subtracting something for the lower bound. And so again, this is what we would call the margin of error. And notice that the only difference between these prediction intervals and these confidence intervals is that in the prediction interval, I just use the standard deviation of the underlying distribution, whereas in the confidence interval, I'm going to use the standard deviation of the distribution of the sample mean. In other words, I'll use the standard error of the mean there. So those are the difference, and just keep an eye out for we're going to look at 2 different types of interval in section 9.2. Now, if we want to make a 95% prediction interval, these are the steps. This is going to be an interval that contains 95% of the most likely outcomes from a random process. So first calculate your level of significance, and for a 95% prediction interval that contains 95% of the most likely outcomes, we're going to put that 95 on the left side of the equation, and on the right side we put 1 minus alpha times 100%. So if I were to divide both sides by 100%, then that cancels. This becomes 0.95 is equal to 1 minus alpha, and that means alpha is equal to 1 minus 0.95, so that means alpha is equal to 0.05. Just like it says right here on the slide. But that's how you would calculate alpha. If you want a 99% prediction interval, alpha is going to be 0.01. If you want a 90% prediction interval, alpha will be 0.1, and so on. So you can use different percents here and get different alpha values. Then we calculate t subscript alpha over 2 using that formula that we talked about. Remember that quantile function is the quantile function for the t distribution, not the standard normal anymore. So let's do that. We'll do second VARS. We go down to number 4 like we discussed earlier. My area here is going to be 1 minus alpha over 2. Well, since alpha over 2 is 0.025, my 1 minus alpha over 2 is going to be 0.975. My degrees of freedom, that's going to be my sample size minus 1. So for me, that's 7 minus 1 because I took 7 measurements. And that is 6. So for degrees of freedom, we punch in 6. Then do paste, then enter, and then we get 2.45. 2.45. So this t subscript alpha over 2 is going to be 2.45 for this example. My margin of error is going to be that times the standard deviation of my underlying distribution. So my standard deviation, well, my calculator tells me that if I go to stat and I go over to one variable statistics, my standard deviation should be, let's see, 2.82. 2.82. And then my margin of error is just going to be 2.45 times 2.82. So we get 2.45 times 2.82, and that's going to be 6.91. So for my prediction interval, the lower bound is going to be the mean minus 6.91. Remember my mean, we calculate as 29.8. And so I'll just round my margin of error, I guess, to 6.9. And so 29.8 minus 6.9, that's going to give me my lower bound, and then 29.8 plus 6.9. So my sample mean minus my margin of error, and then my sample mean plus my margin of error. That's going to give me my upper bound of 36.7. So lower bound 22.9, upper bound 36.7. Oops, that is, don't need that right now. That's going to be the lower bound and the upper bound of my prediction interval, which means that for this random process of measuring my car's miles per gallon, we say that 95 of the most likely outcomes from this random process fall between 22.9 miles per gallon and 36.7 miles per gallon. In other words, if you were to measure your car's miles per gallon and get less than 22.9, or measure my car's miles per gallon and get more than 36.7, we would consider that highly unusual. So it falls outside of my prediction interval. So another way you could think about this is that the very next time I measure my car's miles per gallon, there's a 95% chance that that miles per gallon I measure will fall between 22.9 and 36.7. Okay, like I mentioned, I alluded to this before, my confidence interval means something different. And really what it comes down to is this margin of error calculation, because I still use the same t subscript alpha over 2, so that's still going to be 2.45 just like we did before, but now I use the standard deviation of the sample mean. And so going back to this formula, this standard deviation of the sample mean is going to be my standard deviation, which was 2.82. Now divided by square root of n, which is square root of 7. So let's calculate that. 2.82 divide by square root of 7. And that gives me 1.07. So whenever we get to this confidence interval, my S subscript X bar, that's going to be 1.07. So my margin of error is going to be 2.45 times 1.07. So that will give me 2.62 for my margin of error. My confidence interval is going to be my sample mean, 29.8, minus my margin of error for the lower bound. So I might say, 29.8 minus 2.6. That's going to be my lower bound, 27.2, and then my upper bound should be that sample mean plus my margin of error. So my upper bound should be 32.4. 27.2, 32.4 for my lower bound and my upper bound. And again, the way to interpret a confidence interval is we say the confidence interval contains 95% of the most likely values of the population mean. So remember, we can calculate our sample mean, but we know the sample mean is not the population mean. It's just an estimate of what that population mean is, but it's going to contain some error. So instead, we can make a confidence interval and say that we are 95% confident that the true population mean falls between 27.2 miles per gallon and 32.4 miles per gallon. Now, what's true here is since the standard deviation of the underlying process is always greater than the standard deviation of the distribution for the sample mean, the prediction interval will always be wider than the confidence interval. So in my example that I just did, we found a prediction interval of 22.9 up to 36.7. So here's 22.9 and here's 36.7 on a number line. So the green rectangle represents my prediction interval. My confidence interval had lower bound 27.2 and upper bound 32.4. So my confidence interval is going to be that purple rectangle that's not quite as wide as the prediction interval. And these are both intervals that are centered around my sample mean. My sample mean was 29.8. So keep this visual in your head about the prediction and confidence intervals. So just to recap, the prediction interval says I'm 95% certain that the next measurement I take from this random process is going to fall inside my prediction interval. My confidence interval says I'm 95% certain that whatever the true population mean is, it falls somewhere within my confidence interval. So again, the margin of error for the prediction interval and the confidence interval are different, and this is the way to visualize those margins of error. Another way you can represent the confidence interval or the prediction interval is like this. You say x bar plus or minus the margin of error. And there's one more skill that we ought to talk about here, is how to determine the required sample size for your experiment or for your survey. So this is going to require you to decide two things. Number one, you have to decide on your desired degree of confidence. In other words, do you want to be 90% confident or 95% confident or maybe even 99% confident and so on? And just like we talked about in the previous video, you can't have 100% confidence for the same reasons as in the previous video. And then we also need to decide on our desired margin of error. And remember, it's always nicer to have a smaller margin of error. So we want our confidence to be high, we want our margin of error to be low, but both having a higher degree of confidence and having a smaller margin of error, those will both have to increase our required sample size. But anyways, the steps to doing this, you're going to solve for that alpha. So if you have a 95% confidence that you want, your alpha will be 0.05. You're going to calculate a z with subscript alpha over 2. So remember, when you see the lowercase z, that means the quantile function we're referring to is the standard normal quantile function. then we're going to calculate n using this formula. We say n is equal to parentheses z subscript alpha over 2 times your sample standard deviation divided by your desired margin of error. And then you take that fraction and you square the whole thing. So don't forget to square it here. Now, what I've remarked about in red here is that you actually have to guess what you expect your standard deviation to be in order to use this formula to figure out your required sample size. One way you might do this is you might actually start taking data before you decide on your required sample size. So you might go out and take, I don't know, like 20 data measurements, right? You might go survey 20 people or run your experiment 20 times to get 20 measurements. Then calculate a sample standard deviation, and that's what you could use in this formula to figure out what does your sample size eventually need to be. So we might call that pilot data if you're just using the data to figure out this S. So in any case, that's the formula for n, and after you use this formula, you might have a little bit of a decimal, right? So you might end up calculating that your required sample size is 140.3 or so, right? And so when we round up, this is eventually going to be 141, and that would be our sample size for our experiment or for our survey. So that's the process, and let's work a few examples before the end of this video. Example 2. Suppose we want to we want to measure the average age of a Midland College student, and we know there's like 5,000 Midland College students, so maybe it would be a little bit cumbersome to track down every single student and ask them their age. So instead, we just conduct a survey with a slightly smaller sample size. Maybe we want to sample 1 or 200 students instead. If I want to know the average age with a 99% confidence within a margin of error of plus or minus 3 years, and suppose we go out and we ask 10 or 15 students and we find a sample standard deviation of 8, how many students would I need to survey in order to hit these sort of markers? 99% confidence, plus or minus 3 years. Well, I'm going to have to use my formula in this green box here. N is equal to z subscript alpha over 2 times that sample standard deviation divided by my margin of error all squared. Now, to calculate z subscript alpha over 2, I need to know, well, what is alpha? And so I'm going to solve for alpha by setting 99% equal to 1 minus alpha times 100%. And if I divide both sides by 100%, that gives me 0.99 equals 1 minus alpha. So alpha is equal to 1 minus 0.99, which tells me that alpha is 0.01. Knowing that alpha over 2 should be 0.005, and 1 minus alpha over 2 should be 0.995. Now to get the z subscript alpha over 2, we're talking about evaluating the standard normal quantile function at the point 0.995. So I'm going to need a calculator to do this. I go to second VARS. The standard normal quantile function is going to be number 3, where the area is going to be 0.995, mu is 0, sigma is 1. I do paste, and I find that that lowercase z value is 2.58. So I think I'm ready to use my formula and plug everything in here. So I put 2.58 times, my word problem tells me that I should use s equals 8 for that standard deviation there, my margin of error is plus or minus 3 years, and I need to square the whole thing. So in my calculator, we do open parentheses 2.58 times 8 divided by 3, close parentheses, and then square that, and we get 47.3. Now, of course, we need to round this up. So after rounding up 47.3, we're going to get a sample size required of 48. So for 99% confidence that I have the average age of a Midland College student within plus or minus 3 years, I need to go out and survey 48 students and then average those and take the sample mean, and I can be sure that my sample mean is within plus or minus 3 years of the true population mean, at least with a 99% level of confidence. Okay, last example before we're done with this video. And suppose you want to measure, let's say, the relative humidity in the air. So you hear the newscaster or the meteorologist talking about relative humidity as being, 30% or maybe even 20% during the winter. And in the summer, maybe it's like 40 or 50%. Well, that's talking about how much water vapor is in the air around us. And one way you can do this is using an instrument called a sling psychrometer. So I'm going to take 5 measurements, and then I'll take the sample mean of those 5 measurements and say that that is the true value, or it's at least my best estimate of the true value. Then we're going to construct a 90% confidence interval, remembering that the confidence interval is sort of saying, I think my true population mean, or the true value of the humidity in this case, falls inside that interval. So doing this, I need to use this procedure for figuring out the confidence interval, the one on this slide. So we're going to solve for alpha. We're going to calculate my t value, t subscript alpha over 2. Then we'll calculate the margin of error, and finally the confidence interval, like this. So I'm going to find alpha by setting 90% equals 1 minus alpha times 100%, and then solving this equation using your algebra skills tells me that alpha is 0.1. That means alpha over 2 is 0.05, so 1 minus alpha over 2 is going to be 0.95. Then to calculate my t subscript alpha over 2, that's just going to be my t-distribution quantile function evaluated at 0.95. And remember, my t-distribution wants to know what are my degrees of freedom. And my degrees of freedom are my sample size minus 1. So my degrees of freedom here is 4. So in my calculator, we go to second VARS. We go down to number 4 to get that t-distribution quantile function. My area is going to be 0.95. My degrees of freedom will be 4, and then I paste enter to find that t subscript alpha over 2 value should be 2.13. Okay. My next step as I go about calculating this confidence interval is going to be to calculate my margin of error, which is going to be that t subscript alpha over 2 value times the sample standard deviation of my sample mean. So to calculate this, I need to take my sample standard deviation and then divide by square root n. And so I'm going to take whatever the standard deviation of these 5 numbers would be, and then divide by square root 5. So first step, calculate the sample standard deviation. In my calculator, I'm going to go to Stat and then Edit. I'm going to clear out this list 1 and put in my new values, which are going to be 43. I think my calculator crashed again. Then we will put in our data here. So we have 43, 35, 37, 42, and 38. I'm going to go back to stat, this time go over to calc, and then one variable statistics, down to calculate, and this tells me my sample standard deviation is 3.39. That's for my underlying process here. Now, to calculate that S with a subscript x bar, to calculate that standard error of the mean, I need to take 3.39 and divide by square root of my sample size, which is square root 5. And that gives me 1.52. So that means my margin of error here for my confidence interval is going to be 2.13 times 1.52. So that margin of error will be 3.24. Well, let's call it 3.2. And heck, what was my sample mean? That's important to know. Let's go over to one variable statistics, and we will find the sample mean to be 39. So now my final answer here, my confidence interval, is going to have a lower bound 39 minus 3.2, which should be 35.8. And then it's going to have an upper bound of 39 plus 3.2, which is going to be 42.2. And again, maybe the most important thing about this section is to be able to interpret this confidence interval. And we say that based on my 5 measurements here, and doing a little bit of fancy math, I can be 90% confident that whatever that true value of the relative humidity in the air is, I'm 90% confident that that true value is somewhere between 35.8% and 42.2%. Now, the last thing I'll mention is that there is a little bit of a shortcut on your calculator, and we'll try that out with our last example. But you could, if you want to, try out going to stat, arrow key to the right till we find tests, and then number 8 says t interval. The reason we're using t interval is because this is a confidence interval, and we have to use the t distribution for reasons we talked about earlier. So we select this. You can either input the data from list number 1 with a confidence level of 0.9, or if you wanted to, you could highlight the stats button and click enter, and then it's going to pull up, a place for you to put in a sample mean and a sample standard deviation and a sample size and confidence level. And regardless of which way you choose to do this, at least if you do it correctly, we should get the same answer. This is a nice way of checking our answer too to end the video. And so using the calculator shortcut, we got a lower bound of 35.8, which is what we have here, and an upper bound of 42.2, which is again what we got just a moment ago for example 3. All right, so that'll be it for the new material this week, and I hope you have a great weekend.